All right, here we go. Today we are talking about piecewise functions. We have two goals today: to evaluate piecewise functions and to graph piecewise functions. But before we begin, let's first talk about what is a piecewise function. A piecewise function is a function represented by a combination of equations, each corresponding to a part of the domain. And just a little note for you over here, it must pass the vertical line test, like any function would. Okay, a step function is a function that increases or decreases from one constant to another. So it's just straight horizontal lines increasing, or they could go the other way, looking like a set of stairs. All right, on to example 1, evaluating a piecewise function. So right here, you see our piecewise function, f of x equals, and then on top we have 3x plus 2 if x is less than or equal to 3. And on the bottom we have x minus 1 if x is greater than 3. So really what we have here is two linear equations, two lines. And over here, we have a restriction on the domain. So what this is telling us on the top right here is that if we have an x value that is less than or equal to 3, we're going to use this equation. If we have an x value that is greater than 3, we're going to use the bottom one. So when you are evaluating, we'll start right here with f of 0. So what you need to first decide is which equation to use. 0 is less than or equal to 3. So we are going to use this equation right here. And then all you do is you evaluate it. So you plug a 0 in for the x, 3 times 0 plus 2, and simplify. Okay, the second one, evaluate the function at 3. So again, go up to your piecewise function and decide which of these two equations we're going to use. And again, it's going to be the top one because 3 is less than or equal to 3. So plug 3 in, f of 3. We'll take 3 times 3 plus 2 and get 11. The bottom one, evaluate the function at 6. So now if you look at the piecewise function, you look at the domain restrictions over here and here. Hopefully you will see that, or hopefully you'll know that 6 is greater than 3, so we want to use the bottom equation this time. So we're going to take 6, substitute it in the equation for x. So we're taking 6 minus 1, and we get 5. So that's how you evaluate. First got to decide what equation to use, then just plug the number in. Graphing now is a little bit more difficult. Again, we have two lines. We have 3x minus 4 and negative x plus 1. We want to graph these lines, but we want to limit them. You can see here we're splitting our equations at 2. So maybe to begin, let's start by just graphing this line without worrying about any restrictions. So if you remember slope-intercept form, y equals mx plus b, you always start with your y-intercept, negative 4, and then you use your slope m and count rise over run. So if m is 3, that means we are rising 3, running 1, and we can just keep drawing our line from there. I'm just going to go all the way across again. All right. So there's the first line. Now let's go ahead and graph the second line. Actually, let's do this instead. Let's take a look at our domain now. So our domain here says for x is greater than 2. Well, here is 2, this imaginary line right here. I want this top equation only for the values where x is greater than 2. So if you look on the number line, if I go this direction, all of those numbers are greater than 2. So I only want the right part of that line. So I'm actually going to go ahead and erase that. So I only want this part right here. Okay, I only want the values for x greater than 2. Now, the other thing we need to talk about here really quickly is the inequality. Jumping all the way back to Algebra 1, if we were graphing, you know, for example, if we were graphing x is greater than 2 on a number line, if it's just greater than or just less than, we always used an open circle and drew an arrow. This is kind of similar. Our starting dot here has to be an open circle because we're not including 2 right here. Okay, now on to the second one. So we want to graph negative x plus 1. So again, I'm going to start with my y-intercept at 1. Change the color quick. My slope m is negative 1, so I'm going to go down 1 to the right 1. I'm just going to keep going. Yeah, I'll just keep going here. And I'll go all the way the other direction as well. Okay, so that would be the second equation if this domain restriction didn't exist. But it does exist. I still have my cutoff point here where the equations are changing. It's this dashed line here. So now I got to decide. I want the values less than or equal to 2. So I want everything to the left of that line. So I can actually go ahead and erase this, all of this. And if you look at the inequality, the or equal to part means that we want a solid dot, which I have right here, and we're going off to the left. So there you go. Graph the first piecewise function. There's kind of a lot of steps, a lot of little nuances with it, but all in all, it just comes down to graphing 2 lines and deciding where the split is happening. So let's take a look at example number 3 here really quickly, the last example we're going to do together. So first of all, maybe start by finding the split. We're splitting right here where x is equal to 3. So if you go along the x-axis, find 3. Maybe you want to just draw that split line in there right away so you know exactly where we're cutting these lines off at. All right, let's go ahead and start by graphing x plus 5. The line y equals x plus 5. So you start up here at the y-intercept. So b is 5. My slope m is 1. So I'm starting at 5, and I'm rising 1, running 1. Oh, I'm going all the way to my cutoff there. I'll go all the way through just in case, because we got to decide, do we want the left side of the cutoff or the right side? Okay, now if you look at the inequality, you realize, hey, why on earth did you graph those couple extra dots when you didn't have to? And that's a fair question. So if you take a look, we want less than or equal to. So we're going to include 3, and I want everything to the left. So that means that I can get rid of those 2 dots and make this a little more obvious closed dot, and everything to the left. So there you go. There's the first one. The second one, we're starting at negative 1, and we are rising 2, running 1. So from here, I'm going to go up 2 to the right 1. I'm just going to keep on going all the way this direction. And I can go all the way to the left, but you're only going to have one line on the left side, one line on the right side. They really shouldn't overlap. And then also, if you take a look at the inequality here, greater than 3, so I don't want any of this stuff to the left. And also, just because it's greater than means I want an open circle to start that point. And there would be your second line, piecewise function. We're just piecing together 2, in this case, 2 lines. There are a couple of examples here for you to work on, 2 to be exact. Let's just talk about how do you graph a single number. Okay, that's the line y equals 2. And if I jump all the way back to the beginning units of Algebra 1, hopefully you remember that this is a horizontal line through, I might as well add this as well, the y value of 2. So if I'm looking at my graph real quick, if there was no domain restrictions, it would be that line, that horizontal line through the y, where y equals 2. But again, you have these domain restrictions, so you need to go ahead and limit it and then also graph the second line there.